Okay, so let me start thanking the organizers, Manuel and Hervé. I hope I pronounced them correctly. My French is completely inexistent, so sorry about that. Okay, so I have 3 lectures to present some kind of like a big project that took us some year to finish. My idea is to give an overview of give some of the background today and some of the proofs, and to give some of the flavors of this, how these things about harmonic measure and rectifiability connect to harmonic analysis. So it's really a pleasure to be here in the Institut called Joseph Fourier, because you see I'm coming from Fourier analysis. To me, it's really, really a pleasure. Okay, so let us start with some introduction. So I'm gonna start giving some of the historical background, and then I will explain some of the ingredients that we need to understand this. So this is a result going back to the late 70s, on which Dalbert proved that if you have a Lipschitz domain in Rn+1, I will be working in Rn+1 all the time, then something which is called the harmonic measure, which is, I'll see this in a moment, is an object that allows me to solve the Dirichlet problem, is in some class which is called RH2, which is the class reverse Helder with exponent 2. So what does this mean? This means that not only this object is absolutely continuous with respect to sigma. Sigma is going to be the surface measure on the boundary of the Lipschitz domain. So this is absolutely continuous with respect to sigma, and I'm going to denote k for the Radon-Nikodym derivative of omega with respect to sigma, and you have this reverse Helder inequality, which is telling you that somehow what you have is that this Radon-Nikodym derivative has integrability too. A priori, the only thing that we know about this object is that this is in L1, but somehow in Lipschitz domains, this self-improves into an L2 integrability, right? And this is the kind of, this is saying that what is called the Poisson kernel is in L2, and this is the scale invariant version, because all these things and during these talks are going to be stable when you take your domain and you scale, you move your domain, the results should not depend on the point at which you choose your domain, or even the scale. If you dilate or you compress your domain, the results should be the same. Okay. So why the solvability, the reverse Helder 2 solvability is important? Because this allows me to solve the L2 Dirichlet problem. So I'm going to use L, the calligraphic L, to denote the Laplacian. I know typically you write delta, but delta is going to mean forming something else. And then you try to solve, you look for a harmonic function in the domain omega, so that U restricted to the boundary in some sense is a function which is in L2. So why this is related to the harmonic measure? Because the way you solve this problem is by using this integral representation. The harmonic measure is actually a way in which you can construct function using this. So now you can think that if your function is in L2 with respect to sigma, for this duality pair to be meaningful, you would like this to be in L2 with respect to sigma. Heuristically, this is the idea, right? And that is why you have this reverse Helder 2 here, right? So this is just Helder's inequality. At least heuristically, you of course has to do something else. Okay, so this is for Lipschitz domain. So no matter how bad is the Lipschitz domain, of course, it's not the same to have, say, the upper half space, which is a very nice Lipschitz domain, or to have something which have maybe like a sawtooth or something like that. But the point here is that no matter how bad is your Lipschitz domain, the exponent is always 2. Okay, so the next step consists in maybe looking for more general domains on which maybe you no longer have the exponent 2, and maybe you have something which is of 1 plus epsilon, something which is slightly bigger than epsilon. Of course, by Jensen, this inequality is easier when the exponent goes close to 1. Okay, so the way that I understand the infinity of sigma is the union of the reverse Helder P classes, and the definition is the same. I just replace 2 by P. Okay, and then I can write this in using this solvability in terms of solvability. And now, because this was a duality thing, if I have here P, I have to put here P prime, right? So the idea is that knowing that your harmonic measure is in an infinity is equivalent to show that this is solvable for some finite and probably very large Q, right? So you look for solvability for large Q, which is the same as showing reverse Helder a reverse Helder condition for p very close to 1. P very close to 1 is more likely to happen, right? So that's the idea. If you put a worse domain, you expect to have maybe 1 plus epsilon. Okay. All right, so let me now say what is this harmonic measure that I just introduced in the previous slide. So I'm going to be working all the time in Rn plus 1, where so my MS space is Rn plus 1, and at least n is greater than 2. So this means that my ambient dimension is at least 3. There are reasons to keep the case n equals 2 aside. Probably you can think that the case n equals 2 is nicer because you have complex variables, but from the PDE point of view, the case n equals 2 is more problematic because the fundamental solution of the Laplacian doesn't decay at infinity, and this creates a number of problems. So for me, in order to be safe, I'm not claiming that those results are not true in n equals 2, but to be safe, let's put ourselves in an environment in which the fundamental solution of the Laplacian decays, and this is going to be, for instance, important for the estimates for the associated green function. Okay, so the harmonic measure is not a measure, it's actually a family of measures. It's a family of measures indexed by the points in the domain. And I say probability, quote the probability, because this depends on the domain. If the domain is bounded, the harmonic measure is a probability. If the domain is unbounded and the boundary is unbounded, it's a probability. But you have something like the complement of a ball, then the harmonic measure is not. So you have something like that. Your domain, something like that, the harmonic measure is never a probability. Okay, or at least the way that you construct the harmonic measure. Okay, but this is different in n equals 2. So this is why one of the reasons I'm in dimensional list 3. Okay, so the idea is that you take a function which is continuous with compact support in the boundary. Because I'm considering unbounded domains, I need to consider functions which are continuous and compactly supported. And then you find some way so that given any data, you construct a solution associated to that data. I'm not saying that my data has to agree with f, because unless you put some conditions on the boundary of the domain, you don't expect to have your solution to be continuous all the way to the boundary. But still, there is an abstract procedure. You see, you give me the data, and I construct something that is like the solution with boundary data. And because of maximum principle and representation theorem, you saw that this solution is in the dual of the continuous function with compact support, which is the set of random measures. So that is why I have this probability thing. So for every x, this is what you do, right? So this is the way you construct solutions. So this is our candidate for solution. Okay, so this is a situation. So this is my domain. Maybe it has some cusp, maybe it has some weird places. And then there is this interpretation for harmonic measure, which is interesting. More than interesting, gives you an intuition what's going on, which is the following. So harmonic measure is a measure on the boundary. So suppose that you have a point or a particle that is sitting on x, and then you look for a Brownian traveler departing from x. So this object is the probability that this particle escape through f from the domain. Okay, so you start moving around, and then at some point you escape from the domain. You look what is the probability that it does this through the set f, and this is the harmonic measure. So why is this important? Because in a sense, this is telling you that harmonic measure is connected to the geometry. For instance, you can think that maybe from here you have a high probability to hit the set f, but maybe it's very unlikely to hit this kind of part. Because very likely, because this is kind of narrow, when you start having this Brownian tablet, they're going to get stuck in here. Okay, so this is the intuition. The intuition is that good properties for harmonic measures can only occur if your domain has nice property, and this is actually what we are gonna see. So this is in a sense, some way to connect geometry of the domain. Also, regularity of the boundary, we'll see in a moment, with a PDE property, which is this harmonic measure. Okay. So as I said before, I'm going to use delta. I'm going to keep delta for the notation, which is a surface ball. What is a surface ball? A surface ball is the intersection of a ball with center at the boundary. So it's this kind of thick purple line here. This is what I call a surface ball. And I'm going to use this all the time. And I'm going to assume all the time that this surface ball, by default, I always center at the boundary. Okay? I'm going to use also sigma to denote the surface measure, which is the n-dimensional Hausdorff measure restricted to the boundary. Okay, so as I said before, my domain is Rn+1, and I'm going to think that my boundary is n-dimensional. So I'm dealing with the codimension 1 case. So this is one condition that I'm going to use all the time, is that my boundary is Ahlfors-David regular. So what is Ahlfors-David regular? Says that the surface measure if of any surface ball is comparable to R to the n. So this is like a scale invariant way to say that your boundary behaves like R to the n. But it doesn't say anything about the regularity. This is just about a quantitative behavior. So the boundary, for instance, doesn't get kind of, you have like a very thick boundary that oscillates a lot. Maybe this creates problem with this. So this is telling you something about the size of the boundary, but it doesn't give you information about the smoothness of the boundary. There is this classical example, which is the complement of the four-corner Cantor set, which is purely unrectifiable, which satisfies this Ahlfors-David regularity, and this is a very rough boundary. Okay, so this is not for the moment about regularity. It's about just knowing that your boundary has n dimension in a scale invariant sense. And when I put these things here, I mean that the constant is uniform for every x in the domain, and of course for every radius up to the diameter. And again, this is stable. If I take my domain, I shrink it, I move it, I go here, I take this scale, I go here, I take that scale, right? So the constant is always the same. This is implicit in all my estimates. Okay, so this is for the setting. All right, so let's put some topology in the domain. So we know that, so typically when you say what is a domain, you have to specify what you mean by a domain. But of course, you see, we're assuming that the domain is open. Because the domain is open and this point is on the boundary, I know that there is a ball inside. But I have no control whatsoever on the size of the ball. It can be very tiny, it can be very large, right? It can be at most of the order of R, but it can be very tiny and it can be very close to the boundary. If you think in terms of elliptic PD, you would like to have a proper ball, or a ball comparable to the size of the original ball. And this is what is the corkscrew condition. The corkscrew condition says that there is some point, which this is called the corkscrew point, and some constant so that I can put a ball inside of the same order. And again, this constant is uniform, so this happens everywhere. You can actually write this in a different way, is that this is equivalent and saying that the part of the ball that is inside the domain has comparable measure to the full ball. Okay? So this is the corkscrew condition. The corkscrew condition must be understood as a scale invariant openness, right? So it's a quantitative way of seeing at the domain to be open. Okay, and we can do the same with connectivity. So path connectivity says that given 2 points, you can find a curve. You don't know whether the curve is too long depending on the point. You don't know whether these points go this path goes near the boundary. So that what the Harnack chain condition does for you is to create a quantitative path. So it's has the following property. So you have, given 2 points, you can find a sequence of balls which are ordered in this way, and the one intersects the next one, and in particular you can get this polygonal path, so that the following happens. So the size of the ball, the diameter, is comparable to the distance to the boundary. The far away you are from the boundary, the bigger the ball. So it's in a sense, you are trying to get like a very efficient path joining the points that doesn't get to the boundary. And also what is important is that the number of balls, which is called the length of the chain, has to depend only on the ratio between the distance between the 2 points and the relative distances to the boundary. Okay? So you have control on how long is the chain, which is the same as controlling how long is the path, in a sense. Okay, so let's put a couple of examples on which you don't have the corkscrew or you don't have the Harnack chain. So here it's clear that I cannot have a corkscrew because I cannot insert a ball here, an interior corkscrew. Right? This is so narrow that I cannot put a ball. The measure of the part of the ball that is inside the domain is very tiny, so I cannot find this constancy here. And this doesn't have the Harnack chain. Why? Because look at these points. So the ratio between the distance of the points and the distances to the boundary is like 1. But because the ball that you start have to have radius comparable to distance to the boundary, as I'm moving closer, if I take this point and I'm moving closer to the boundary, I need more and more balls, and I need to go around. So you really, when you get too close to the boundary, your chain has to be very large. So this violates this condition of the number of balls. Okay, so these are the enemies. So these are the enemies, are cusp and places that are kind of close in distance, but are the distance, if you move within the domain, is large. So this is what violates this thing. Okay. So this is the notion that Jerison and Kenig introduced in the 80s, that a domain is Coral domain. So CAD means for Coral domain if it satisfies the interior corkscrew and Harnack chain. This is an interior condition. Satisfies an exterior corkscrew. What is an exterior corkscrew? Is the same condition but on the exterior of the domain. So I will need a ball in here. And also the boundary is Ahlfors a bit regular. So what is NTA? NTA, it only talks about the domain, and Coral is when you also introduce this Ahlfors a bit regularity. Okay? And I'm gonna, you see, this was kind of the thing that was developed years ago. I'm gonna introduce also what is called a one-sided Coral domain, on which the only thing I'm dropping is the exterior corkscrew. That looks very naive, but actually changes a lot. So having an exterior corkscrew or not changes a lot of the, for instance, the regularity of the boundary. And this is what we are gonna see. Okay. All right, so. I think that probably is the same thing. So I don't know if Sem's condition, I'm not that familiar, but maybe Sem's condition says something about the flatness of the boundary. Yeah. It says something because, yeah, it is. Yeah, because you have just two-sided corkscrew. You have two-sided corkscrew. What you create is the big pieces of which is subdomains. But if you have the Harnack chain, you actually create an interior domain, which is better. But it's related. Okay. Okay. So this is what they proved. So David and Jerison in the 90s and Sems independently in 89 showed that in a Coral domain, you have actually that the harmonic measure is in A infinity. So this is the next step, right? So you have Lich's domain, you have Ravenshelder with exponent 2, and now what you have is exponent with some given exponent p that is going to depend on the parameters and on the constants that are involved in this condition. But still, this is the same as saying that you have solvability for some dp prime, or in particular, in particular for some finite p, as I mentioned before, right? And this is because the same duality game that I said before. If the function is in LP prime, this has to be, morally speaking, in LP. Okay? So this is for Coral domains, and my question is, can we go beyond Coral domains? So why do we have to, if we are solving an interior problem, why do we have to assume something on the exterior? That sounds weird, right? If you have a domain and you are solving something in a domain, why do we have to assume that the exterior, in a sense, is kind of thick? So remember that, in a sense, corkscrew tell you that there is the exterior, and the interior corkscrew tell you that there is some thickness inside, right? Because you are preventing these things to happen, right? If you assume something on the exterior, this is telling you that your exterior domain is thick, in a sense. Actually, can be measured in some instances. So the question is, can we remove the exterior corkscrew? Looks very naive, but you'll see that actually we cannot. Okay? All right. So let me remind you the definition. One-sided Coral is Ahlfors regularity and only interior openness and connectivity, and Coral domain is the same thing plus an exterior openness. Okay? So this is in the heart of the proof of David and Sems, David and Jerison and Sems, that when you have interior and exterior corkscrew, your domain is uniformly rectifiable. And this is about regularity. So this thing about having like one ball inside and outside tell you that the only way that this can happen if your domain is kind of flat. In what sense? So this is the definition of for rectifiability, is what is called big pieces of Lipschitz images. So what is this? So let me not look at the definition, but the idea is the following, is that so what this is saying is, for any of these balls, there is a Lipschitz image that agrees with the domain, with the set E. So E doesn't have to be at this point a domain, it's just some closed set which is orthogonally regular. So you know that there is some, maybe there are parts that are not in the Lipschitz image, but you always have a bound from below. So maybe there is a 1% of your set E agrees with the Lipschitz image, or maybe 1 over a million of the domain, but it's the same everywhere and for every scale. This is a scale invariant. This is the scale invariant version of rectifiability. What is rectifiability? Rectifiability means that your set is contained in some union of Lipschitz images, but you don't have control on the Lipschitz constant, you don't have control on how many Lipschitz images here. So here this is telling you that you have some control because the constant of the Lipschitz image is under control. So this is about regularity or about flatness, depends how you want to look on this. Okay, but there are some other conditions about rectifiability, uniform rectifiability, which are interesting. For instance, a set is uniformly rectifiable if and only if it's alpha-double regular and all nice singular integral operators are bounded on L2 with respect to the sigma measure. So this means that this is, in a sense, the most general setting on which you can do Calderon-Zygmund theory. And by nice singular integral, I mean those that have a smooth kernel which is odd and has the right homogeneity. Or you see there is this, what it calls the Davidsen's conjecture, which is, this is true not all for, you can replace all nice singular integral operators by the Riesz transform. This is the Nazarov-Tolsa-Borber result. And also that is going to appear in a moment is also this thing. This is the single ledger, which is the operator that you create using the fundamental solution of the Laplacian. So uniform rectifiability is comparable to the L2 boundedness of the two derivatives on the single ledger, which is the fundamental solution of the Laplacian. So as you see, the uniform rectifiability has this connection with geometry. There is this connection with analysis. There is also this connection with, for instance, being close to the hyperplane in a big pieces sense. This is the using, for instance, the beta Jones numbers. Okay? So this is going to appear in a moment. And this is why it's important. This is the single ledger, which is an integral operator that you use the fundamental solution of the Laplacian. So this talks to the Laplacian. So that is why if you want to do PDs with the Laplacian, this is an appropriate guy. Okay? All right. Okay. So now let me present the following thing. Remember that I said before, can we remove the exterior corkscrew? The answer is no. Because we have the following thing. Assuming that my domain is one-sided core R, only assuming interior corkscrew and connectivity, the following are equivalent. The domain is core R, meaning that there is exterior corkscrew, that's the condition that is missing, if and only if the harmonic measure is in an infinity, if and only if the boundary is rectifiable, uniformly rectifiable in the sense that I presented before. Okay? All right, so how is this proof? The proof was the 1 implies 2 was the result that I put before David Jerison and Sems, and for 2 equals 3, that was a result in 2014 by Steve Hofmann, Ignacio Rierto, and myself. So what we used was to apply a local TV theorem to show that this operator, remember that I put before, that characterizes uniform rectifiability, is bounded on L2. And here is crucial that in a sense you are starting with something which is a infinity, and this is going to be the way that you construct your B function, your accretive system here. The point is that this operator talks to this thing, and that is why you the things relate in a good way. Okay? And this is, as I said before, uniform rectifiability. So actually we proved this equivalence, but later we realized that they are actually even, and this is more about geometry, assuming these conditions, uniform rectifiability of the boundary, regularity of the boundary actually forces the exterior corkscrews. And this was a joint work with Jonathan Sam, Steve Hofmann, Kai Nystrom, and Tatiana Toro in 2014. Okay? So this is for the Laplacian. So my question is, can we work with elliptic operators? Is there a class of elliptic operators, more general operators, that allow you to capture this geometry? This is a connection between PDs, topology of the exterior, or geometry of the boundary, right? So the question is this only true for the Laplacian, or can we prove something more general? So the first problem, and this is actually, you see, it took us a while to figure it out, because the proof that you used was very much for harmonicity. This uses harmonicity because this is a harmonic guy. So it was not possible to maybe consider other operator because it was not even, you see, we tried several years and then we couldn't prove. So we needed actually a different approach. Okay. All right. So this is the class of elliptic operators that I want to consider. So it's going to be a divergence form elliptic operator. A is going to be a matrix, variable coefficients. I'm going to assume symmetry just for convenience, but we don't need symmetry. And then being elliptic means this thing, means this accretivity things from below. So gamma is, this lambda number is greater than 1. And this is just the fact that the coefficients are bounded. Okay, so this is the class. So now we are doing with variable coefficients. And so and then associated with this, much as we did for the harmonic measure, you can define what is called the elliptic measure, which is the same thing. It's an object that allows you to solve the classical Dirichlet problem. Okay, so let me give you results on which knowing something for the metrics tells you something about the elliptic measure. So this is what is called the Kenig-Pipher operators. So Kenig and Pipher show that in a Corral domain, if I write delta to denote the distance to the boundary, these two conditions imply that the harmonic measure is in A infinity. So this is that the gradient of A times the distance to the boundary is bounded, and this Carlson condition. So this is a Carlson measure. I'm going to write this in a moment. So if you don't know what is a Carlson measure, you will see in a moment. Okay? So this is telling you that, okay, you have some control oscillation near the boundary. It can be very bad because it can oscillate like 1 over delta. This is a little bit stronger than having 1 over delta. But somehow this is telling you that near to the boundary, the oscillation can be it has to be a little bit better than 1 over the distance to the boundary. Okay? So this is just in this direction. So this is the natural class for which we would like to get this characterization. Much as we did for the Laplacian, if you put the Laplacian, this is a constant coefficient operator. Of course, this is true and this is true. So the question is that, can we prove a characterization for these operators? And now having variable coefficients tell us that the method that we used before using nativity theorem is not available. So we have to come up with a different method. Okay. All right. So let me now state what is the class of operators that I'm considering. So I'm going to say that the operator is of a KP operator from Kenig and Pipher if, first of all, this is local ellipsis so that I can take the gradient. I'm assuming that the gradient of A times distance to the boundary is in L infinity, and I'm assuming that gradient of A squared distance to the boundary is a Carlson measure. This is the definition of a Carlson measure here. So this is a full integral. So I typically do I make a distinguish between one integral and two integrals. When I do one integral, it's typically because I'm integrating on the boundary, which is an n-dimensional integral, and when I'm integrating here, I'm integrating in the domain, which to me is a solid integral. Okay? So this is a Carlson measure says that this is, which is an n plus 1 dimensional object, behaves like an n-dimensional object. Remember that this is on the boundary, which is n-dimensional because of the Ahlfors regularity. Okay? So Carlson measure is a measure which lives in Rn plus 1 that behaves like an n-dimensional measure. That's the way to understand this. Okay? So this is the Kenig-Pipher condition, and this is the result that I want to prove in these 3 days. So given a one-sided Corral domain, if L is one of these Kenig-Pipher operator, the domain is Corral if and only if the harmonic measure is in A infinity. Okay, so 1 implies 2 is already the Kenig-Pipher result, and the question is this 2 implies 1, which is a joint work with Steve Hofmann, Svetlana Mayboroda, Tatiana Toro, and Zhao. Okay, so this is the goal of the 3 things, and you see this has been like a hard problem because it was kind of we had to kind of create new techniques and new ideas to do it. And you see what I like about this is that I have three talks, and I'm gonna use I'm gonna prove this in 3 steps, and each step is different from the other. So it's kind of like a progressive thing from one step to another, but the techniques are kind of different. So that's what I like about this. Okay, this is just about another way to write the result in terms of solvability for finite p. So this is just a repetition. Okay, so strategy of the proof. Okay, this is my background hypothesis. I have this Kenig-Pipher condition. So let me write gradient of A, this star norm for this Carlson measure condition. Okay, so the goal, remember that what I want to show is that the domain is Corral, but the only thing that is missing is the exterior corkscrews. So rather than what we did in the paper with Steve Hofmann and Ignacio Uriarte was to solve uniform rectifiability, which is in a sense more difficult than solving exterior corkscrews. They are equivalent at the end of the day, but somehow exterior corkscrews is a more geometric object, so you can get more information from that. Okay, so there are three steps. So first, we saw that it has constant coefficient. That was already in the previous slides, but I'm going to present this using a different approach. So actually, in a paper with Steve and Tatiana Toro, we proved this for a little stronger condition, which is gradient of A being Carleson. Gradient of A being Carleson together with this is stronger than this, because you can always remove from gradient at the distance to the boundary. But the idea is that this is valid for something which is not non-constant. So it's not based on the TV theorem. It's a new proof, which was useful for this kind of thing. And then, so this is the first thing, which was already known, but probably to me it's interesting to see the proof. The second case is to show that this is true whenever the constant is, whenever this is small. So this is sometimes happens in this business, is that you know how to prove things when something is small. So if this is small, what you are saying is that your matrix is not oscillating that much. So it's like thinking that you are close to a constant coefficient operator. So you have more chances to prove your result. Okay? And we are going to prove this by a contradiction and a compactness argument. So from the logical point of view, the proof is kind of like understanding what we are doing is not, you see, it's probably kind of like a weird, but then you will see that then at the end of the day, what you are doing is kind of like a natural. And then once you have this for a small, and this uses, because in this compactness argument, you are going to show that your operator converges to a constant coefficient operator. So this is where step one takes place into the proof. And then the last step is to consider the large constant case, on which you just assume that this is finite, and this is a bootstrapping argument. So once you know that something is true for a small Carleson measure, you create some kind of extrapolation, which is like an inductive procedure, right? So you start with epsilon, go to epsilon, 3 epsilon, n epsilon, and then you exceed this constant. So that's somehow the idea. Okay? The three steps have three different proofs. They are different, and each of them is based on the previous step. So that is why I would like to present this. Okay. So my goal today is to give the strategy of the proof. So I'm going to use slides today, and then the other two lectures are going to be on the board. I'm probably going to use maybe the projector a little bit to put some of the notation. But anyway, so I'm going to do it for the moment. This works for any constant coefficient operator, but let me work with the Laplacian, because it's already the same. It's the same argument, right? So my operator is the Laplacian. So the goal is to show that now this is the harmonic measure in infinity implies the exterior corkscrew. Okay. So because the domain is Ahlfors regular, it's a space of homogeneous type, and then you can find some dyadic grid. We can use maybe Vogt David Sem's book, or maybe Mike Cree's dyadic cubes. Okay? So this is just a collection. These are no longer cubes, but they are objects that have the same properties that the cubes have in Rn. So they have the very same properties. Okay, it's like a organization of the boundary. And then I'm going to introduce the collection of bad cubes with some constant C naught. So what is a bad cube with respect to the constant C naught? A bad cube is a cube so that the corkscrew, exterior corkscrew, fails with this constant C naught. Remember, there was a constant the constant is the size of the ball that is in the so if this is this and this is the cube, so this is the length of Q. So failing is that you cannot take a ball inside in the exterior with size C naught the length of Q. This is what I mean by failing. Okay? And then I'm going to show that these bad Qs satisfy a packing condition. A packing condition is a Carleson measure condition, right? So it's the following thing. Suppose that I'm going to show the following. I look at all the Q primes which are bad and dyadic with respect to cube, and I measure the sigma of Q prime. I'm kind of counting or summing all the measures of the cubes that are bad. And I want to show that this is uniformly bounded by sigma of Q. This is, again, this is a discrete Carleson measure. And I claim that it suffices to show this. Why? Because of the following. So first of all, I claim the following. Suppose that I have proved this. Give me a cube, and I can show that there exists a cube which is bad with size between length to the q and 2 to the negative n. Why? Because if not, what happens is the following. I have the first generation. The cube is bad, so it sums like sigma of q. I have all the children, but I'm summing, if all the children are bad, I'm summing all the children again. I have the third generation, right? So every generation, if I don't have a bad cube, I'm summing them all, right? So after m generations of not having this, from here I'm gonna pick m sigma of cube. So this means that there has to be 1, otherwise this is gonna be violated, right? Is that clear? So if I have a lot of bad cubes from here to the great-great-great-grandchildren, it means that for every generation, I'm summing sigma of q, sigma of q, sigma q, sigma q, m times. So at some point, I have to pick 1. Otherwise, I will exceed this constant. So this means that there is this thing. Okay? But now, this is just a rescaling thing, because now I know that there is 1. The n is fixed, and this is comparable. So what happened is that I know that q prime has a c, because it's not bad, it's good. It means that I have a exterior corkscrew with constant c naught. But then it has a c, but this means that it has a different corkscrew constant with a different constant, because what I'm saying is the following. So I have here, so there is going to be a q prime, and here I have, in this q prime, I have exterior ball. But what is the size of this ball? The size of this ball is like c naught, the size of this cube. But the size of this cube is comparable to the length of q. So then with a different constant, have exterior corkscrew. Okay, so that's the proof. So as you see, showing that it's not a direct proof saying, no, I'm going to show that all cubes are good. I'm showing this packing condition, which as the end is saying that all cubes are good with a different constant here. Okay? All right, so this is our goal. So you see, we are thinking about geometry, but now we have a thing which is about analysis, right? So I'm reducing my proof to show that something is a discrete Carlson measure. Okay, so this is our goal, so that these bad cubes satisfy this packing condition. And then I'm using what is called a Johnny-Nemeth reduction. And that's actually is a very easy exercise. The following suffices. I need to show the following. I need to show that for every, this should be a, this is not this D, this should be a blackboard, like a math BBD. So for every dyadic cube, I need to show, if I show that there is a family, which is going to be a stopping time family, of pairwise disjoint cubes, so that the following happens. First of all, if I take the q naught minus the union of the qj's, I get some constant. So it doesn't cover the whole thing. So I have some maximal stopping time cubes that they don't cover the whole thing. They leave some space. And then I know this Carlson condition when I'm restricting to the cubes that are on which I haven't stopped. So I'm thinking I have a big cube and I'm stopping and stopping. I'm thinking all the cubes that are before I stop. So this is this family. The f of q naught is the cubes that are not contained in any stopping time cube. So this is saying that in order to show that something is Carlson, it suffices to show that it's Carlson when you restrict to this family of stopping time cubes, provided you have some lower from below. Okay? So this is telling you that you don't have to look for all the cubes. You just have to do something for some cubes that are going to be nicer. Okay? So that's the idea. And this is a real variable thing, doesn't have to be with PD, something like that. And the proof of this is really easy. It's really, really easy. If somebody's interested, it's a really easy exercise. Of course, once you know what you have to do, it's a very, very easy thing. It's really, there is no trick. It's just looking what you have here and then passing and hiding something on the other side. It's very elementary. Okay? So then, remember, I want to show a packing condition. I'm reducing matter to show a packing condition, but for some cubes that have good properties. And now I have to pick those cubes. So my point is that I need to pick a family having this property and this property for which things are correct. Okay? All right. So let me now fix a dyadic cube. And I'm going to call, this is going to be because I have the interior corkscrew condition, I'm going to call X naught, say, a corkscrew condition relative to 100 Q naught. 100 it means I need to send my point, my pole a little bit far away so that there is no problem with the green function. Okay? There is this estimate, what is called Burgen's estimate, that says that harmonic measure of Q naught is some fixed constant. This is, if you think about probability, this is saying that, so this is Q, this is 100Q, the corkscrew is going to be here. What this is saying is that you have some probability of reaching the cube Q. So in terms of this probability approach that I mentioned before, this is what this is saying. Okay? So this is an estimate. So we have an estimate from below. All right. So let me normalize matter. So let me call omega to this thing multiplied by sigma of Q naught and multiplied by this constant capital C naught. And let me write this calligraphic G for the same thing, and this is the green function. This is the green function for this domain with polar X naught. Okay? All right. So because of this normalization, first of all, I have that this is smaller than 1, I have a smaller than C naught. This is the normalization, this is this constant here. Okay? So I have, this is my top cube, and I know that the average of the Q naught of omega with respect to sigma is between 1 and C naught. So now this is where I'm going to do my stopping time argument. I'm going to start subdividing, and I'm going to stop when this average gets either too big or too small. Okay, so I subdivide dyadically and stop when this gets too big or too small. Okay, this is a stopping time thing. This is more or less the same thing that we do when we saw that the dyadic maximal function is with type 1. But in that case, you only look where the average is greater than lambda. If you think what you do to show that the maximal operator is bounded, this is just showing that the average is greater than lambda. Right? This is the same thing, but now you have like two criteria for stopping your for getting your stopping time cubes. Okay, so by construction, this is a pairwise disjoint because this is in the nature of being a maximal family. If you haven't stopped, your averages are like 1 because remember, I have a stop whenever this gets too small or too large. So in between, before stopping, I have this thing. Okay, remember that this is a notation to show that Q is not contained in a QJ. Or in other words, these are the Qs on which I haven't stopped. And then this is where the A infinity comes into the picture, and this is what it doesn't come into the boundedness of the with type maximal function, is that if the harmonic measure is in A infinity, you can actually show that this is a bound from below. So this is my family. Remember what I said before, if you go to the previous slide, I needed to show a family, pairwise disjoint, and I needed to have a bound from below, and I need to show this packing estimate for this family. So this is what I'm going to do because I have the candidate of my family. So I have this condition what I need. What is the goal? What is the advantage? That I know that like these averages are like 1, but if these averages are like 1, it's the same that the green function is like the distance to the boundary, and this can only happen if your boundary is flat. So this is somehow the philosophy. Okay. All right, so let me try to get to that. All right, so let's fix a cube which is bad and is above this family, and let's put some smooth cutoff of the ball associated to cube. Because the cube is in this family, remember that these averages are like 1, right? Okay, and that's because the harmonic measure is doubling. In this setting, I can put this cutoff thing. Okay, so now I'm using this representation formula, and this is the way that harmonic measure connects to the green function. This is like a representation between harmonic measure and the green function. Okay, so this is just an integration by parts argument. So you have something like that, and I'm going to do the following. I'm going to add and subtract some vector here, right? So I put here minus beta, and here I put beta, which is a constant vector. All right. But because this is a smooth cutoff, the integral of the gradient in the whole domain is 0. So I can replace the domain with a minus by the exterior domain, right? Because I have the full integral is 0, and the full integral is equal to the integral inside the domain and the integral outside the domain. The boundary has measure 0, right? So in particular, I can put this. So I'm bringing in the exterior domain, okay? And now I'm going to put absolute values inside, and then this is going to give me the gradient of phi is like the length of q. Here I'm going to put the gradient of q like the length of q to the negative 1, and this is what I keep, right? So this is because it's supported here. I have these two terms, right? And I'm going to estimate both of these terms. Okay, so sigma of q for the moment is controlled by this. So what happened? And remember, I have brought to the slides the exterior domain. So if the cube is bad, remember if the cube is bad, it means that there is no exterior corkscrew. If there is no exterior corkscrew, it means that this part of the measure has a small measure. Remember, this part of the ball, remember that I said before that having a corkscrew means that the measure on the part of the domain is comparable to the ball. So here, because I cannot use this means that it has to be small. That's the only way that it can happen. Okay? So this is what I'm bringing here. So I have beta, which is going to be a uniform number, and this is because the cube is bad. There is nothing on. There is no enough mass on the exterior with constant C0, which is at my choice, right? And then I can write this because of the alpha-W regularity. I can write in this way. Okay. So this is what I do for the exterior part. What I do for the other part is make this the composition. So I'm going to do the part away from the boundary and the part near the boundary. So I put something like an epsilon length of q here. This is kind of like a simplification of this, and the point is like this is going to be very like a narrow boundary strip because this is going to be uniformly under uniformly control. So what is the measure of this? This is going to be height times length, right? So this is like length sigma of q, and this is like epsilon length of q. So this is what I get from here. This is uniformly bounded. This is the height, epsilon length of q, and this is sigma of q here. So this is heuristically what is going on. Okay? And the only thing I need to do is 1. So for 1, let me kind of skip some of these things. For 1 is a Poincare inequality. Okay? So these things this part that is away from the boundary can be created so that it has some kind of connectivity. So you can do like a Poincare inequality within the domain. And then because you have a gradient, so you pick beta, which is the constant that you have to pick so that you have a Poincare inequality, and this is what you saw. Okay, this requires some work. This is going to depend badly on epsilon, but that's all right, because epsilon is going to take place it's going to take care of the other part. Okay, and now what you have this, because also this is a part which is away from the boundary. In the part that is away from the boundary, I know that the distance to the boundary is like the length of q, okay, with constant dependent on epsilon. And I have this is the Caffarelli phase modulus alpha estimate, which says that g over the distance to the boundary is comparable to the average. But remember, I'm in one of these cubes in the above the stopping time family, so this is like 1. So this is saying that g is like distance to the boundary, which is like the length of q. So for free, I can insert here a green function. Okay. So I repeat here, g over the distance to the boundary is comparable to this. But remember that my q was in this family here. So I know that this is like 1. So I'm saying at the end of the day that g is like distance to the boundary, and the distance to the boundary is the length of q. So this is just what kind of makes this homogeneous. Okay? So I have been able to get into this point. All right. So let's summarize what we have. So remember, if q is bad and is in this class of stopping above the stopping family, I get this from the exterior, this from the part near the boundary, this from the part away from the boundary. Okay? I pick first C0 smaller than sigma, very small, so that I can hide in this side. Then I pick epsilon, and then I hide. At the end of the day, by hiding things, this is what I get. Okay? So I've been able to control this by sigma of q by this thing, right? And now remember that I have to sum over all these cubes that are bad, and I'm gonna just make the union of these guys, right? This is some star here which is irrelevant here. Okay, so this is what I create, and now my goal. Remember, I'm summing this Carlson condition, and I'm becoming to an object which maybe is interesting because these are solutions of the problem, so I can integrate by parts. So the idea is now that I can do this is just like a some algebraic conditions. I can do an integration by parts, and at the end of the day, I integrate by parts, and this is what I pick on the boundary. This is the divergence theorem. I can use the divergence theorem here. I'm cheating a little bit because I have to probably move a little bit up, but that's all right. So this is just an integration by part. This is just look at the beginning, so I can get an estimate on this in terms of something that happens on the boundary. And now to finalize this, remember that G over distance to the boundary, I mentioned that before, is comparable to this depending on epsilon. But this is like 1, right? So because I have a constant coefficient operators, and this is the first place on which I'm using constant coefficient operators, I know that the gradient of the green function is like the distance to the boundary. This is not true for general variable coefficient operators. But I know that G over delta is like 1 because of this condition. And I can do the same here because I'm also using, maybe this part is okay, but what happens is that if you have something which is harmonic, the derivatives are harmonic. This is something that happens only with constant coefficient operators. If you have a solution for a variable coefficient operator, the derivative is no longer a solution. But here it is true, right? Something is harmonic has all derivative which is harmonic. So I can use the same trick and then compare by G over distance to the boundary, which is like 1. So finally, I put all my pieces together. Remember that I have this solid integral controlled by this. And then all those are controlled by 1. So then I pick the Hausdorff measure of the boundary. And then you can see that this has the right estimate, so it has n-dimensional ADR. So then you get this, and this is what we are done. Okay? So, and this is all for today. Probably, you see, it's probably went a little bit over time. But you see, that was kind of, yesterday I'll try to maybe be a little bit more slower, but this is one of the techniques. At the end here, this is the way in which you connect geometry with analysis. Remember that my goal was to show something about the geometry of the stereo. I've been able to put this in terms of some packing condition, which is a Carlson condition. Then I do like a stopping time argument to put in some good cubes, and then I use a integration by parts argument. So you see this is a combination of geometry, harmonic analysis, and PDEs, because we have integration by parts. Okay, so this is the thing. Tomorrow, the first lecture, I'm going to consider the case of a small constant, and then the techniques are going to be different. It's going to be like a compactness argument is going to be different, and then the last day is going to get back a little bit to this Carlson measure things, but it's going to be a different proof. And I think I'm done for today. Thank you.